Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillahir Rahmanir Rahim. Do you have any questions from last time? What did we cover last time? Yes. Accuracy. Well, what was the main topic? Accuracy was just a concept. Yes, Muhammad? How to choose features in what? In building decision trees. Okay, in building, how actually the main topic last time was how to build the decision tree. And how was it? How do we select the feature? Yes, Saud? Okay, so we take each feature and we compute, if we ask a question on that feature, what will be the accuracy given the answers or given the value of that feature, right? And we do that for every feature, select the best. Then what should we do? After we select one feature, what do we do?
Check it.
Raise your hand, please. Yes.
Check if it has all the values.
Yes. We check if we stop or not, right? And we stop if all the values in the remaining data, right? Because we split, right? We take the subset of the data. If all the values in the remaining data have the same label, then we should stop and predict that label. Or what? If we run out of questions or features, right? If we run out of features in that path, right? Because we have to complete all the paths of the tree, right? Okay, so that's an overview of the training algorithm, and this is the pseudocode for the training algorithm. Okay, so quickly we'll not go through the details here. The algorithm that you have in the slides and also the textbook. We start with the guess. Okay, so whatever the data that we have, we have to pick the most frequent one as the guess, and we check the two conditions that we just mentioned. Okay, if the data is unambiguous, if all the data is the same, or if we don't have any remaining features, so we should stop and return back the prediction. Now the prediction is the guess, the majority in the data that we have. If that's not the case, then we look at the features that we have. We split the data. Here we have two for each feature. We assume that we have binary features here, so we have just two values for each feature. Of course, this is a specific case, but we can generalize it. For each feature, we get the subset of the data. Remember when we highlighted some rows in the data set? So this is like highlighting the rows for the no value and highlighting the rows for the yes value. And then we compute the score for that feature. Okay? What we did in the last lecture, we used classification accuracy as the score. Okay? But we said that we have other ways, and we'll explore that inshallah. So we compute the score, which is the majority vote in no and the majority vote in yes, and then we pick the best feature, and then we split the data. Okay, we split the data on that feature, and we continue building the tree from that point. Okay, remember here we have binary features, so we have two subtrees, right? Because we have two values. So for each value, we'll have to continue the tree. Okay, so this is a recursive algorithm. So we'll call again the same algorithm, which is decision tree train, to build the tree from that point. Okay, based on the new data, which is whatever the left or right subset, whatever the no or yes subset of the data, and the remaining features. Okay. We exclude, of course, the feature that we just picked. So this is the training algorithm. Okay, so this is the pseudocode for the training algorithm. For the prediction, it's much easier. Okay, so we go through the tree, right? We start from the root. So given the tree, again, this is also recursive. So we stop if we reach the leaf. So if we reach the leaf, then we should return, of course, the whatever prediction is at that leaf. And if not, then we should either go left or right based on the value of the feature in that test point. The test point here is the example that we want to predict. Okay, so we want to predict the label for that point, for that example. So based on the values of the features, we go either left or right. Of course, here again, we assume that we have binary features. If we have features that have more than one value, of course, we need to branch more than 2 branches, right? So here we have just 2 branches. We either go to the left if the feature is no, or go to the right if the feature is yes. Okay? If we have more values, of course, we have to do multiple if statements or maybe switch statement or something like that. Okay? Any question about these two? So this is for prediction. We call it also inference in machine learning. So whenever you hear the word inference, it's very similar to the word prediction. Okay? So we are trying to estimate or to predict the label for a given example, and the previous one was the training algorithm. We call it a different way in the first 2 or 3 lectures. Do you remember? This algorithm, this type of algorithms, here it is called training algorithm, but actually in general it is called what? Is that the training model? Huh? Yes. Learning algorithm. Very good. That's one example of a learning algorithm. Okay, so that's a learning algorithm for decision trees. Okay, right. Where is the learning model? The decision tree itself that we get from this. Okay, so the decision tree itself that we train, that we built, is the model that we will use for prediction. But this is the algorithm. This is how we learn this model. So this is called learning algorithm in general, or training algorithm. Okay? Fine. Now I want you to think together. You can discuss together maybe for a couple of minutes. What are the pros and cons of decision trees? What are the advantages and disadvantages of decision trees based on what we discussed so far? What are the advantages? What are the good things about decision trees? And what are the bad things about decision trees? Okay, I'll give you a couple of minutes. You can think together, please, and talk together, and try to come up with advantages and disadvantages. Okay, let's get back here and tell me, what did you come up with? What are the advantages? Let's focus on the advantages. Yes, just one.
It doesn't require much computational power.
For what? For training or for inference?
For inference.
For inference. Okay. So for prediction, it's very fast, right? Because we just may need to probably ask one question for one feature. If we have few features, then it's very fast, right? So that's an advantage. That's an advantage. What else? Yes, Sulaiman? Advantage, positive thing. No advantages? Decision trees are very bad, like that. Nothing? Yes. Ahmed? Ahmed, right?
Visualizing prediction.
Very good. We can visualize the prediction. We can see the tree. We can visualize the model, not just the prediction. We can see the model. Okay? And this is very important feature. Yes, Magid?
Yes, I have one pro and one con.
Okay,
I think
so let me finish this first, okay?
Okay.
Okay, so the visualization is an important point, okay? Not every learning model can be easily visualized, okay? There are many complex models that it will be very hard to visualize. Type. If we say it's easy to visualize, we can also say it's easy to understand, right? And if you look at the decision tree, you can easily understand you can easily interpret the decisions that was made. Okay? So if I tell you that the classification for this example is yes, then you can say why the model said yes. Okay, you can go through the tree and say, okay, yes, that's because this feature is like that and that feature like that and so on. Okay, so easy to visualize, easy to interpret, and easy to understand also. I think understanding the way that decision trees are built is also an advantage, right? Okay, Magid, do you have any more?
Yeah, yes, sir. It's direct and simple. It's this is a pro for the decision tree. It's direct because it has a direct features. Like we know which feature is for what, and it's simple because it's not so complicated. We can draw it easily by extracting the data from the data sheet and extract it in a drawing. So it's simple. The
Yeah, so
concept.
we covered that it's simple and easy to understand and to visualize. Anything else? Yes.
Yeah, the cons, I think
No, we didn't get to the cons yet. Okay, yes.
Oh, okay.
Remind me of your name, please. Muhammad.
We can say we have a clear path, we know the end.
Clear
Clear path.
path.
Yeah. We know all the passes we will.
Yeah, again, it's easy to understand and to visualize, right? So that's.
We know all the leaf and we know all the end points.
Yeah. So this is called, by the way, this is called white box classification. We see everything in the model. There's nothing that is hidden or complex. Okay, we see everything. So that's a big advantage. Now about the cons, what are the disadvantages? Yes, Omar. But that's not specific for decision trees, right? That's for any supervised learning algorithm. We need labels. So I cannot say that this is the disadvantage for decision trees in particular. Sulaiman? سعود. تعودوش جنب بعض. سعود. That's an artifact of that example, that specific example with the learning model. But in general, it can work with multiple branches. It doesn't have to be only two. Actually, we had in our example a feature that has three values. So that cannot be.
Still limited. We can't apply it in a lot of.
Okay. What we covered so far, we assume that the features have discrete values, right? Okay, but what if the feature is continuous, is numeric? Okay, we didn't cover that. So in this case, we might have multiple branches. Okay, we didn't cover that, but so far, yes, it's limited if we only have what we call categorical features. Okay, we'll talk about that later, inshallah. Yes?
It does work with numerical features.
It does work, yes, it does work, yes, but we didn't cover that yet. What are the cons? How about if you compare the time complexity of the training versus the prediction? Training will take much more time. Okay? Yeah, training is really expensive in case of decision trees. Okay? There are algorithms that are very fast. We'll talk about that. Okay? In training. But this one, no, it takes a considerable amount of time. How about if we did any changes in the data? What will be the effect on the decision tree? Yani after we trained, let's say that we had some data, we trained, we got a decision tree. And then we realized that, okay, there was a mistake in one example. Would that make any difference in the decision tree? Someone, yes, what's your name?
It does because.
What's your name? Azam, okay.
I think it does because if it's connected, if it's near the root, then it could affect the other branches.
Exactly. We might need to retrain the entire. Actually, yes, generally we have to retrain the entire decision tree, even if we have small changes, because the splits, the decisions that we made to split the data is based on the values, right? If the values change it, then we might need to retrain. How about if we add more examples, not just change the values? Yes.
All the probabilities.
Not features, examples.
All the probabilities will be different.
So
We will have to retrain again.
So yes, everything will change because all the scores that we computed in general scores that we computed might change, right? So we'll have to retrain. Okay. Of course, if we get new features, again, so this is inflexibility, right? So if we have a situation where the data is coming over time, it will not be easy to use decision trees because we have to retrain the data, the tree every time or multiple times. Okay. I think we covered good number of advantages and disadvantages, at least up to that point, based on what we covered. Inshallah, I think we will get back to it later, probably after the next lecture, because in next lectures we will talk about some practical issues, so we will get back to that. Yes?
Tamer, I think the decision trees are slow as a cone. Because we have to
Slow
wait for
in
each
what,
decision,
Majid?
each feature.
Slow in training or in prediction?
I think, sir, in prediction.
Actually,
Because
compared to
we
other.
have to wait for each feature to be executed and see what other options or other features that we have to that are available to us, and then choose one, and then we have the other.
Do we have to go through all the features in prediction? No, it depends on the path, right? It depends on the values. So in many cases, you might stop very early. That's why it's actually fast. Okay, but in some cases, of course, you have to go through all the features. But even that, if the number of features is small, then the tree will be really small and will not be deep, and you will not have much time. Okay, so we discussed the first learning algorithm, which is decision trees. Okay, now we'll before we go through another learning algorithm, we'll stop a bit and try to see how now we can formalize the machine learning problem in general. Okay, so we'll give a quick or simple formal definition of machine learning. Type. The way that we will see it is a machine learning as a function approximation. Function approximation. So what do we mean by that? Here's the setup that we have in machine learning. We have a set of possible instances. So we have we are observing some examples. Okay, this is the data that we have. Okay, so that's given. We have also a set of labels or classes. Of course, here we are talking about classification as an example of machine learning. So we have a set of possible instances, we call it X. We have a set of classes, we call it Y. And we also have or want to approximate a specific target function that we don't know. So that target function actually maps from the training data, from the data, the instances, to the labels. Okay, is that the decision tree that we built? No, that's the actual optimal function that actually maps the data, the values of the features to the label. Okay, what we built is just an approximation. Yeah, the decision tree that we built, of course, it's not optimal. It might not be the actual real function that maps from the input to the output, that maps from the feature values to the labels, but it's just an approximation. Okay, so there is a target function, but we don't know it. If we know it, then we are done, right? If we know the target function that maps from the input, the instance, or the X to the labels Y, then we don't need to learn anything, right? Because that function will tell us the label for that example is 1, the label for that example is 0, and so on. Okay, so we don't need to learn anything. But the main machine learning problem or challenge is that we don't know this function and we want to know it. Okay, and of course, what we will be able to do is to get a function that approximates that function, that target function. Okay, so the target function here is denoted by F star, and we have set of function hypotheses. We have set of possible models that we can learn. So many models we can learn, right? right? If you remember for decision trees, it wasn't just one decision tree that we can get. We got one because we used a specific learning algorithm, right? But it's not the optimal, and it's not the only one. So we have actually a set of function hypotheses or set of models. Type. The input, so this in a sense is not just the input, is all possible examples that we can see in real life, okay? But the specific input to the machine learning algorithm is a specific set of training examples, okay? Every training, of course, the x's in the training examples are some or subset of these possible instances. Okay, we call that x1, x2, x3, and so on. And for each one, we have a label, if we are talking about classification. Okay, so x1 has a label y1, xn has a label yn, and so on. Okay, with me so far? Now, what should be the output? The output should be a specific hypothesis that best approximates the target function. That's our hope, that from the learning algorithm, we will get a hypothesis or a function that approximates the actual real function that we don't know. Okay? So if you think about it, we are trying to approximate something that we don't know. So that's the biggest challenge in machine learning, that we are trying to get something that we don't really know, but we can learn something about it. Okay? From, of course, the training data that we have. Type. If we think about decision trees, if we try to formalize the decision tree training and prediction as we have on this slide, as a function approximation, what will be the possible instances? Examples with feature values, right? As we saw the data set that we used in the playing tennis data set. Okay, so we had for each day we have some feature values. Right? So we can think of every instance as a feature vector. Okay, vector of values, one value for each feature. And the labels, of course, were the classes that we want to predict. Okay, so and of course the training. How about the set of function hypotheses? All possible. All possible matrix, but it's specifically in decision trees. All possible? Not labels, no. Not branches. Okay. Fine. Let me explain that again. What do you mean by set of function hypotheses? These are all possible models that we can learn in general. Okay. Remember that every model here will be a function, right? Like a function. So in this formalization, we are learning functions. Type. We have to have a space of these functions, right? We want to get one that is good enough. One among so many. Okay? That's in general. In decision trees, what is the space? Space of what? What do we learn in decision trees? What do we learn? The model is represented as what? As a tree. As a tree, right? The model is a tree, right? So the set of function hypotheses here is the set of all possible trees. Set of all possible trees. Okay? That's if we are talking about decision trees in particular. In general, they are functions, but the function in decision trees is represented as a decision tree. Okay, as a tree. So the space of all possible solutions or all possible models in decision trees is the space of all possible decision trees that we can learn. Okay, and the one that we get as an output is the one that we get using the learning algorithm. Okay, is that clear? So we will formalize any supervised learning, supervised machine learning problem as we have here in the slide. We have set of possible inputs, okay, possible instances, sorry, X, labels. We have unknown target function that we want to approximate, and we have space of possible functions. Okay? The input, the specific input is the pairs, the labeled examples, right? We have specific training examples, not all the possible instances, of course. We don't get all possible examples in the world, right? When we train a model, we don't get everything. We get some examples. So this is the training examples, of course, from the unknown target function. And our goal, our output, is the function that best approximates this unknown function. Okay, is that clear? Right. Now, to learn a model, we need to know at least two things. Yeah, Ahmed. Okay, two things. The first thing, how good or bad the predictions will be. How good or bad the predictions are. How can we know that our predictions are good or bad? The second thing, how we can model the data. How can we have a mathematical model of the data? Okay, so we will discuss these two things next. The first one is the loss, is how we know that the performance or the prediction of the system is good or bad. We do that using a very important concept in machine learning called loss function. Loss function. What do you mean by the loss function? It's a measure of error. It's a measure of error. So if the error is high, then the loss function should give us a high number, a large number. Okay? If the error is very low, then the loss function should give us a small number. Okay? So for example, the simplest loss function, specifically in classification, is as follows. Okay? So what is the notation here? L represents the loss function. F of x, remember f is the function that we got, the model. Okay, the model that we are training. Okay, which is the decision tree that we get from the decision tree learning algorithm. So f of x is the prediction for the example x. Okay, so that's the prediction that the function will give us, that the decision tree will give us in decision trees for the example x. Y is the actual label for it. Y is the actual label for it. So the loss function always take two parameters, the predicted value, the predicted label, sorry, not the value, predicted label, and the actual label. And then compares somehow between these two. In this case, the loss function will be 0 if the predicted value is equal to the actual value, because that means that our prediction is correct. Our prediction is correct. So the loss function will give us, in this case, 0. Remember, the loss function, even from the name, loss is 0 here. We didn't lose anything. Our prediction is correct. There is no error. Okay? Remember always that the loss function is an error function. It's an indication of an error, or a measure of error. And 1 otherwise. Otherwise means, in this case, that the predicted label is not equal to the actual label. Okay? Type. So that's just an example of a loss function. Notice that the loss function is a function on one example. Okay? So it gives us an indication or a measure of error just for one example. Type. Is that the only loss function that we can use? Of course not. It depends, the choice or the design of the loss function depends on the goals of learning or the type of learning. So for example, if we are trying to predict the age of a person from its social media profile or his photo, okay, and let's make it that simple. From the photo, I want to predict the age. Okay, so this is classification or regression? Regression type. Now, imagine that we used this loss function for that problem. What will happen?
It's not good.
It's not good. Why?
Because you could, for example, if he's 35 years old and you expected the model predicted 34,
it will give 0. Yes. So whenever the two values are not the same, it will give 0. Okay? But for this specific problem, which is the age prediction, of course, getting close to the correct age should not be as problematic as being very far. And if I predicted 10 years old for 35 years old man, that's very far, right? That's much worse than predicting 33 or 34 out of 35. Okay, so in regression, that's not a good loss function. Okay, so we'll talk about good loss function for regression. You can think of it, of course, but we'll talk about it inshallah later. But keep in mind that the choice of the loss function is very important, and it depends on the type of learning, the goal of learning. What are we learning? Okay, and how do we want to model how far our predictions are from the actual the true predictions, not the true predictions, true labels. Okay, clear? So that was the first one. The second one. So from now on, we assume that we have a loss function. Okay, and of course for classification, it can be that simple. Fine. Now the second question. How can we model the data, or where does the data come from? For this formalization, we'll assume that we have a probabilistic model for the data. Each example of the data has a probability to appear in real life. So we have what we call data generating distribution. We'll assume that there is a probabilistic distribution that by which the data was generated. Okay, and of course you are familiar with what we mean by probability distribution, right? Okay, so we will assume that for all the x and y pairs, every pair of x and y, what is x and y? What is x and what's y here? X is an instance, is an example, which is a feature vector, okay, and y is the corresponding label for that example. Okay, so every x and y pair, we'll assume that it has a probability to be seen, to be observed. Okay, type. Where does this probability come from? From a specific distribution. The distribution that generated the data that we see. But do we know this distribution? It should be given. If it's given, then the learning will be easy, right? The prediction will be very easy. Right? If we know that distribution, that we don't need to learn anything, right? We know for every value x, there are some possible values y, but we can maximize, we can see which one is the highest probability, and then we can predict it. Okay? So we wouldn't be in that class if we know the distribution. Actually, we don't know this distribution. But we assume that there is a distribution by which we generated the data. So we don't know what D is, of course. But what we only have is sample data from that distribution, which is the training data. That's all what we have. Can we assume that the training data is everything? Of course not. Of course not. Okay? Even if we have a very large amount of training data, of data that we can collect. Remember, in classification, for example, we need labels, right? So labeling this data will limit it, of course. We'll not be able to label millions or billions of examples in general. Okay? So we will have really small subset of examples, but we will assume that these examples are all coming from the same distribution, but we don't know that distribution. Okay? So remember, D is the generating distribution, and we don't know it. Now, in order to, since we assumed here that every x and y pair has a probability, right? So we can compute the expected error of our model based on that distribution. How is that? We compute what we call expected loss. Now, the function that we will need to learn should produce good predictions, right? which means that if we computed the loss over all possible instances of XY pairs in our domain, then this number should be small, right? So we should minimize it, right? So we want eventually to learn a function or a model that have small expected loss. Okay? Why we said expected loss, not loss? Because we have a probability distribution here, right? So we'll have to estimate a value, okay? So we'll have to compute the expectation, okay? The kind of weighted average, okay? So the expected loss here, and we will discuss this now, but the expected loss is indicating the how good the function that we got is. Okay. Of course, as the expected loss gets higher, that means that the predictions are bad, right? Fine. The expected loss will depend on the loss function. Remember from maybe 5 minutes ago, we said the loss function is defined for one example, right? Now we assume that the data has a probability distribution or degenerating distribution behind it, so we can know the probability for each example. So the expected loss is the sum over all pairs from that distribution of the probability of each pair and the loss value for that pair. Right, let me explain it again. So eta here is what we call the expected loss. Okay, we want to compute the expected loss over the entire data. Right? That's what we want. We want a model to have a very small expected loss so that we can know that the predictions are really good. Right? Because they are very close to the actual labels. Right. E here is the expectation over this distribution. Expectation of the loss function, because we want to estimate the loss, right? So expectation of that function means that if you remember the expectation, if I gave you the any probability distribution, so please get back to statistics here, okay? You will see a note, I think, in the textbook. It will remind you of the expectation. But the expectation of any probability distribution, what is the meaning of it? If I took, so that the meaning of it, the informal meaning of it, if I get a random value, yeah, if I get a random value from that distribution, what will be the value? Okay, that's the general meaning. Okay, right. That depends on the probability of each value. Okay, that depends on the probability of each value. Of course, the getting random, I mean, I need to repeat that experiment multiple times and get the average. But the how it's computed is that we multiply the probability of that value times the value itself. That's in the expectation formula. If I want to compute the expectation for a specific function over a distribution, then I need to multiply the probability of that example. So d of x and y is the probability. D is the probability distribution, right? So d of x and y is the probability that I can see that example times what? Times the loss function, the loss value for that example. Okay? So y is the actual label for that example, and f of x is the predicted value. So if we do that over all possible values of x and y, then we can estimate the loss value for that function. Okay? Right. Now, can we compute this actually? Do we have everything for us to compute it? Do we have all the value that by which we can compute this? We don't have d, right? We don't have d aslan. Okay? So if we know d, then we can compute this, of course. Okay? So we'll know how to actually compute an estimated value of this, inshallah, next time. Okay? Thank you.